cette thèse à Rome, à la Sapienza.
Exactement.
Donc, il va nous parler de milieux granulaires en vibration. Et il sera là cet après-midi si vous voulez discuter avec lui. Voilà, c'est à toi, je te laisse la parole.
Super. Donc, bonjour à tous et à toutes. Je vais faire mon séminaire en anglais. Et first of all, thanks for the occasion to share these results that mostly come from my first postdoc that I did at LPS. So we'll talk about self-assembly and non-equilibrium dynamics in vibro-fluidized granular system. But first, I want just to introduce a bit better myself. So I started my academic career in Rome with my PhD, where I focused on simulations and theoretical models to describe the emergence of collective behavior in vibrated granular materials. Then at the beginning of 2022, I moved to France, where I started this transition between simulations toward experiments. And here I built a setup to perform studies on self-assembly and absorbing phase transition on vibrated granular materials. And now I'm still at Laboratoire de Physique des Solides, but in the MOA group, so I changed the group. And I'm focusing, I'm also focusing on other type of soft matter systems. So today I will talk about results coming from my first postdoc and also some ongoing projects that are still rooted in these projects. But before that, I just want to give you an overview of what I'm doing right now in the MOA group. So I'm focusing on friction in interleaved systems and viscoelastic foams under mechanical vibration. So the main project I'm involved is this one, in which we are revisiting the experiment of interleaved books that develop a quite interesting phenomenon of sample amplification of frictional forces that have been explained based on simple mechanical arguments now 10 years ago. But now we are revisiting this experiment, focusing on the emergence of stick-slip dynamics in this kind of system, where you have at the same time deformation of your object, but also self-application of friction. And in particular, we are interested in linking the stick-slip features we can extract by tracking the single events in a traction machine. So the experiment is taking, two blocks of post-it. You interleave them page by page, and then you try to pull them. You can do that also with a book. And you will find that there is an extreme resistance towards pulling and separating this object. This is because you have a lot of interface in contact. When you try to pull, you also, since you are pulling from the part that is thinner than the central block, then you will also compress the system. And by compressing the system, you are also increasing a lot the normal force between each interface. And so if you do the maths of that, you realize that there is a factor that goes with the exponential of the number of page square between the initial friction that you have between the first two pages and the total one. So basically, you have, even with like 30 pages, you have a factor exponential to 30 at the power 2 of 30, so it's a huge amplification. And basically, what I'm doing now is like to really study this detachment dynamics that occurs with the stick-slip, but somehow try to interpreting what is happening in a single stick-slip event by linking this with the deformation we can study in the system. So you see that in each stick phase, the system compresses, and then it releases stress by jumping, by doing these slip events. At the same time, I've been also involved in the PhD project of Alice Requier, who did these nice experiments that use the same setup I built for granular materials, but now to vibrate foams. And here you see that when you start to vibrate these foams that are made with a continuous phase made of yield stress emulsion, you see that initially they destabilize through coarsening, so gas diffusion across the film that divides the bubble. But at certain point, you see this huge coalescent cascade, so destabilization driven by the thin breaking between the foams. And so my main contribution in this project was to propose a statistical model that was able to describe macroscopic observable related to foam destabilization, such as the decay rate of the number of bubbles, and which is able to disentangle the role of these two, the contribution of coarsening and coalescence in foam destabilization. So this was just an overview of what I'm doing now, but now let's switch to the main subject of the seminar, which is granular materials. So I like to define this granular material as macroscopic systems composed of macroscopic particles. So this means that the building block of this system, which are the grains, are themselves macroscopic objects. So they interact between themselves with forces that are dissipative, and this somehow is quite and I mean, they're quite ubiquitous in both nature and applications. And the aspect that is very interesting about this material is that they behave at the collective level either like fluid or solid, depending on the external conditions. And so this kind of the emergence of this complexity is really important, both for understanding them as a material that is involved, that is present in many situations, but also for fundamental science, because it's interesting to try to link the behavior at the single particle scale to the emergent one. So the particular way of fluidize granular materials I'm interested in is what you can do when you apply mechanical vibration to this kind of material. So when you have granular materials, you apply vibration, you have this phenomenon which is called vibrofluidization, so you are fluidized thanks to vibration, and this, of course, impacts on both mechanical and rheological properties of this system. So this is important. As you can see here, I'm showing an example coming from industrial application where you have a vibrating sieve that indeed, thanks to vibration, is able to make this system flow toward in the device, and then inside the device it divides grains of different sizes. And you can understand that somehow this kind of process is very important, and without vibration you would be able to do this in an efficient way. So when you see this kind of dynamics agitation at the level of the grains, you could be tempted to do a quite bold analogy, and for example, taking systems which are colloidal suspensions. So you still see this kind of vibration, and you still have systems which are colloids that are much bigger than atoms because you are in the micrometer scale, but somehow you have this idea that at the end, if some colloids are dispersed in a fluid, they are able to thermalize with the surrounding fluid. And so you have the so-called Brownian motion of the colloids. And somehow you could be tempted to do this analogy. Okay, maybe vibration is doing to granular materials what temperature is doing to colloids. The fundamental difference between these two cases is that in colloidal suspension, actually, the way the system explores its configuration space is really ruled by equilibrium statistical mechanics. So you can really think about colloids as big atoms that are able to thermalize with the thermal bath, and basically just somehow link the microscopic properties to the macroscopic one thanks to a statistical mechanics approach. So by weighting statistically the configuration of the system starting by the Hamiltonian of the system and the inverse of the temperature. On the other hand, when you have granular materials, a priori there is not a well-defined Hamiltonian in your system if you want, and so it's not possible to use this kind of tools to link microscopic to macroscopic behavior. However, I will show you that still this analogy can be useful in some examples, while completely somehow wrong in other examples. So this is the outlook of the seminar. So in the first part, I will talk about self-assembly and fake coexistence, so phenomena that involve the spontaneous formation of crystalline patterns in vibrated granular materials. And in the second part, I will talk about absorbing phase transition, which instead involves the problem of injecting energy in a granular materials thanks to vibration. So let's start from the first part. So I was telling you that indeed the usual equilibrium statistical mechanic approach is not valid a priori for this system. However, if you look at some experimental works, you can find a strong analogy between like what happened at the granular scale, at the micrometric colloidal scales, with regard to this phenomena of pattern formation of crystalline structure. So here I'm showing you the results coming from an experiment that was just considering taking a system of monodispersed spherical grains, you put them on a substrate and you start to vibrate, okay? And you repeat the experiment by taking every time more spheres for a fixed volume. So basically you are increasing the area fraction of your system. And basically, around a critical area fraction, you can observe a transition between a stationary state in which the particle prefers to remains in an amorphous and disordered state to a state where the particles prefers to arrange in these hexagonal crystals. This is in the y-axis. Y-axis somehow is an observable which is a proxy of the pressure, or what you would define as a pressure in your system. Okay, so in both axes is basically the equivalent. It's something you can extract from the G of R of your system. So it's the local density. So what is remarkable is that you can do the same experiment with colloidal spheres on a substrate, and you observe almost quantitatively exactly the same phenomenon. So, but in this case, basically, you can really interpret this crystal as a phase that is stable from the thermodynamic point of view. So that minimizes some free energy, while in this case, you cannot, because there is not this free energy defined a priori. So questions that can arise from this example are, for example, how far can we actually extend this analogy between colloidal and granular crystallization? And can we, for example, form more complex structure that are predicted by thermodynamic equilibrium? Because you can still see that basically this is the most simple structure you can think of when you have monodispersed objects. So in order to tackle these questions, I will start again from an example coming from colloidal systems. So here I'm considering a study that has been done in my group before my postdoc, where they were considering this system of colloidal spheres on a substrate. The main ingredient here is that they are considering a binary mixture, so spheres of different sides that are doing basically Brownian motion on a substrate. And the main control parameters that they considered are still the area fraction, so the total area occupied by the spheres when you look them from above, the number ratio between the two species, so the number of small spheres over the total, and the size ratio between the two spheres. So by doing numerical simulation of this system with the dynamics which is compatible with the colloidal suspension, so with equilibrium, with the thermodynamic equilibrium assumption, they were able to self-assemble a rich variety of different crystalline structure by varying the fraction of small spheres and the size ratio between the species. For today, we'll just focus on these two phases. So the first one is a 8-fold symmetric quasi-crystal, which is a rather complex structure that I don't have really the time to introduce here. Just basically, to introduce it briefly, is a structure that relies long-range orientational order, but without any periodic cell that repeats itself. So it's like an aperiodic crystal. While this other phase is kind of simpler, it's just a binary crystal whose unit cell is this square made of 4 large spheres that surround a small sphere. Okay? So the question is, okay, now these structures are predicted at the microscopic scale by thermodynamic stability. Can we actually realize this structure at the macroscopic scale? Okay, so as I was telling, taking again the example I was doing at the beginning, now we take grains vibrating on a substrate. So somehow we are going from the microscopic to the macroscopic scale and using vibrations instead of temperature. So we want to realize a system at the macroscopic scale which has the same geometrical constraints, but now letting it explore the configuration thanks to vibration. So this is what we did what I did in the beginning of my first postdoc. So I built this experimental setup, which consists of an electrodynamic shaker that converts an electric signal into a vertical displacement, and then we attach to it a quasi-2D cell in which we confine our granular mixture, and then we can, of course, taking image of the system and follow the evolution of the structure as a function of time when we apply vibration. Okay, so the idea of the experiment is the one. So let's take a system that has the same area fraction, concentration of small particles, and size ratio that we know for colloids allows to stabilize this kind of structure. We realize this mixture at the macroscopic scale with granular spheres. We prepare the system in such a way that there is no relevant order emerging in this structure, and we can check this by the structure factor of the system that we obtain by doing basically the 2D spatial Fourier transform of the coordinates of the grain. And we saw this ring structure. That means that there is no relevant order in the system. Then we apply this vibration and this sinusoidal shaking, and we ask ourselves, we will be able to form the same structure, which is kind of complex in the sense that in order to form this full structure, you need first to locally form these motifs and then order this motif in such a way to have a structure factor that reveals these eightfold symmetric Bragg peaks. And the answer is yes, indeed. By doing extremely long experiments, so this is a self-assembly process that takes a lot of time, we were able to stabilize this quasi-crystalline structure by mechanical vibration. So basically, we do see, indeed, if you just see the snapshot, it's not so clear. It's kind of an hidden order, but then you look locally and you see that indeed you have this kind of motifs that are formed. So you have, like, for example, here 4 large particles that surround a small one, and here you have 4 large ones that with this other lead square made of 4 small ones, and here you have a kind of a triangular tile. And so this lead to the first observation of quasi-crystal self-assembly beyond the micron scale. So not self-assembled thanks to Brownian motion, but thanks to this way of injecting energy, thanks to vibration. So now I will focus on a simpler phase because basically I want to study the transition I expect by varying the overall area fraction of the system, so by varying the density of the system between an amorphous structure to an ordered structure. I do expect a transition also based on this prediction from colloids. So to study this more complex phenomenon, we wanted to focus on a simpler phase, which is this square binary crystal. So again, we perform first the self-assembly experiment. So we place ourselves in the same geometrical condition that at the colloidal scale lead us to the formation of this of the crystal. We apply vibration and we observe, indeed, by waiting a lot of time. These are very long experiments. So the one before was taking like 10 days to self-assemble. This takes like a few days. And at the end of the experiment, I do see the stabilization of these crystalline patches in my system, okay? That spontaneously self-assemble. So if I can follow, actually, I can basically define the fraction of particle belonging to this crystalline structure and follow this as a function of time, and we check that it's indeed stable. So for almost basically 1 day, this number stays stable. We can check the overall mobility of the system that is decreasing, so really telling us that while crystallizing, particles are also less able to rearrange, so they're kind of solidified. And here I'm showing you just a snapshot of the single unit cell of this system, which is made of 4 large grains that surround a small one. So once that we know that we can self-assemble this system on high densities, now we started to decrease the density of the system. So this is, it looks kind of the similar condition, but there are less particles in the system. So you have a slightly lower area fraction. And when we do the experiment, we see that still starting from an amorphous structure, we stabilize a phase where we have a coexistence between a crystalline patch with an amorphous structure. And when we look at the video we really see that the crystalline part is also more is like solid, while the amorphous one is liquid-like. Indeed, in this part you have a lot of rearrangement of the particle, while once you are in a crystalline configuration, you are kind of blocked, so you are solid. And you can also quantify this with the mobility map. So now we can put together many experiments done at different packing area fraction, and really observe a transition between a condition where we are not able to stabilize any ordered structure to a condition where we stabilize crystalline structure, and in between there is a stable coexistence region where you have the coexistence is between the solid and the fluid. And so a way to interpret this phenomenon is really to do an analogy with a liquid-solid first-order phase transition. So what you basically expect when you have a solid at the melting point. So you have you can stabilize a condition where you have stable coexistence between the solid phase and the liquid one. Okay, and I just want to remark that is somehow stable. I mean, having stabilized this kind of pattern for granular material is non-trivial at all, because you have a binary mixture, and you know that in granular materials, when you have binary mixtures, you have the tendency to side segregate. While in this case, the fact that the crystal is stable allows the system to have perfect the two species that are perfectly mixed. Okay, because in this, for example, in these patches, you have the equal number of large and small grain. So to somehow confirm this scenario, I also performed a numerical simulation based on the discrete element method. So basically, we rebuilt in silico our experimental setup with this simulation method that still consider grains as spheres vibrating on a substrate, and then you allow these grains to interact with the realistic contact models. And basically, you can perform simulation in which you stabilize, indeed, the coexistence between the crystal phase and the amorphous phase. And for example, you can study how different observables behave across this interface. For example, here, I'm plotting the local density of the system, and we do see that the crystal phase is actually denser than the fluid phase. This is something we do expect. So somehow, the fact that you can stabilize this coexistence in numerical simulation is really a proof that this analogy with the first-order phase transition is appropriate. But now I'm showing another observable that I can extract from numerical simulation, which is the so-called granular temperature, which is nothing but the kinetic energy of the system in the XY plane. Okay. And I do see that across the interface, there is a difference of this kinetic temperature, so that the crystal is hotter than the fluid phase. And this happens in the stable configuration. And this somehow is counterintuitive for two reasons. First, if you think of the analogy with thermal equilibrium, you would never stabilize any phase which has a stable temperature gradient, because you will always tend to thermalize. But also coming from the granular community, you would have expected that the denser phase, so the crystal, would have been colder, not hotter, because usually when you are denser, you have a higher collision rate, collisions are dissipative, and this would tend to lower the efficiency of energy transfer. So when we saw that, we say, this is nice, because at the same time, we have something that is completely thermodynamic equilibrium-like, and when you look at dynamical observable, it's completely deviating from thermodynamic equilibrium. So the qualitative argument we had to explain this relies in this idea that on how energy is is transmitted to the system from the vibration source. So here we see that we are injecting actually energy in the system in the vertical direction. So the only way the system can transfer the energy in the XY plane is by collision between the grains, okay? And we do see that the most efficient way to transfer this vertical energy into the horizontal plane is by small, large grain collision, because the small one can hit the big one from below and transfer better this energy. Now that we noted that, we also see that indeed the crystalline structure optimizes large, small grain contacts, while in the amorphous region, you have much more probability of having particles of the same size, one close to the other. And particles of the same size are statistically undergo collision that are less efficient to transfer energy from Z to XY. So when you realize this, indeed you realize that there is indeed an interplay between the local structure of your system and the efficiency of the energy transfer that you have from the vibrating source to the granular medium. And this, again, is something that is a striking deviation of the thermodynamic equilibrium picture, because once you have, for example, a colloidal system and you thermalize it with a thermal bath, no matter of the local structure, you will always thermalize with the temperature of the bath. While here, somehow the temperature you reach depends on how you are locally enraged. So this is a true granular feature, if you want. And within the PhD project of Raphael Mer, we also checked this idea of coupling between energy transfer and local structure within the framework of some simplified collisional models that can be treated within the framework of kinetic theory. And we actually proved, we actually verified this picture by analytical prediction of how is this kinetic energy as a function of the packing fraction. And we do see that close to the transition that we have between the fluid phase and the crystalline phase, we actually have this jump. I don't report here the equation of that because I didn't have the time to introduce the theoretical framework, but this is a really analytical prediction compared to simulation. So to conclude this first part, the messages are the following. So we can start, actually, in some condition, we can really start from complex pattern and structures that are predicted by thermodynamic equilibrium, for example, at the colloidal scale, and realize this at the macroscopic scale by keeping the same geometrical constraints by using vibrations instead of temperature. We can actually interpret the phase transition between amorphous and crystalline structure we obtain at the macroscopic level within the framework of a liquid-solid first-order phase transition that allows for a stable coexistence between the two phases. But then, as we look at the dynamical observable, this analogy somehow breaks down, and we have really to take into account the mechanical, the mechanical mechanisms with which you can transfer energy to the granular mediums from the vibration, which involves this coupling between local structure and energy transfer mechanism. And here I'm just to show you that in terms of like ideas to continue, it would be interesting to study how this kind of crystalline structure can be used as acoustic material with this line of research that studied how to arrange granular system in order to control sound propagation in a medium. And now that somehow we proved that you can create stable crystalline structure also with binary mixtures, somehow this this allows for exploiting the stability of the structure to explore mechanical properties of more complex structure that you can create with binary mixtures and not just with grains of the same size. So now I switch to the second part of the talk, in which I will talk about absorbing phase transition, which involves this idea of how I can give energy to a granular system thanks to vibration. The theoretical and numerical part are still within the PhD project of Raphael Mer, and the results I'm going to show also come from 2 internships projects of master students. So to introduce this part, I just want to show you that I'm using this exactly the same setup, but in another driving regime. So all the things I presented up to now were in a regime where the vibration were at relatively high frequency and low amplitudes, in which the system basically is mostly confined close to the bottom plate of the quasi-2D cell. So particles do not explore so much the vertical space that is available. And here they do a Brownian-like dynamics that indeed is good to study self-assembly and non-equilibrium coexistence. However, if I keeping the same vertical shaking acceleration, but going to the opposite regime, so now I go to lower frequency and high amplitudes, I enter in a completely different regime in which particles now can explore the full vertical space that is available. So you have this kind of dynamics for which a single particle that, for example, start with some energy in the XY plane, start to move horizontally, but doing a lot of collision back and forth between the upper plate and the bottom plate. Each time it collides with the plate, it loses energy because of tangential friction between the grain and the plate. So a single particle isolated will travel a bit in the XY plane, but that it will eventually end its motion with no energy in XY plane and just bouncing up and down between the two plates. At the same time, if two particles that are traveling in the XY plane at some point collide, during this collision, they can actually exchange now energy from the Z direction to the XY. And when you see them from above, they undergo what we call active collisions. So if you want, in this way, you realize a system which is an active system, but for those of you who are somehow familiar with active system, now the activity is not self-propulsion, so that move the particle, but is an energy injection that happens a collision. And so you have this competition between horizontal damping and active collision that rules the energy transfer mechanism between vibration and the granular medium. So now I show you what happens when you take this system and you vary the density of your system. Here I'm considering monodispersed granular systems with in a much more dilute regime with respect I will show you before. And so basically what happens is that if you take your system at low densities, basically the probability of undergoing collision is low. So basically you are in a situation where the tangential dissipation between the grain and the plates dominates. And so basically you arrive in a stable state in which all the particle has no energy in the XY plane and they're just jumping up and down between the two plates, okay? While above a critical packing fraction, I do observe a transition where I have frequent collision, so there is enough chance to undergo collision that transfer energy from Z to XY, and so I can stabilize an active state in which there is a finite amount of energy in the XY plane. So, and then I can basically extract the number of active particles, the average number of active particles in the steady states, and observe indeed a transition as a function of the area fraction. So this is a so-called absorbing phase transition. So it's a transition between states that are absorbing states that can be dynamically reached but not left, and so which is somehow is a conceptual framework that unifies different phenomena. You can think about gambling. So you use money to have more money, but if at some time you do a bet and you lose all your money, you don't have any other money to get money back if you want. At the same time, in epidemics, if once of the population is dead or immunized, the spread stopped. There is no way to recover. And at the same time, in our granular system, you have this thing that once all the energy in the horizontal plane is lost, the system cannot be reactivated. And so these are paradigmatic case still of critical phenomena of phase transitions, but now in which we have intrinsic irreversibility given by the fact that you are entering in an absorbing state. So you are in an these are called non-equilibrium critical phenomena. So now I show you what happened in our system if we do a phase diagram in which we consider the variation of the area fraction and also of the vibration amplitude, okay? So I'm still plotting here the fraction of active particle in the steady states. And I do see that varying the area fraction, I observe something that I expect. So for low density, I'm in the absorbing state with no motion in the horizontal plane, while at large densities, I'm in the active phase. However, if I consider the variation of the vibration amplitude, I observe something strange, because basically, varying the amplitude of the shaking, I can go back and forth between active states and absorbing states. This means somehow that the vibration amplitude is not the good parameter. I mean, is acting in a non-trivial way on this phenomenon. And a hint that we need to study a bit more what's happening in the vertical dynamics actually as a function of the amplitude is that when you see, for example, a video from the inclined view, you see some grains that are kind of synchronized between themselves. And so somehow in the next slide, I will focus on the vertical dynamics to better understand what's going on here in the horizontal somehow activity. So we performed an experiment with a single particle in the quasi-2D cell, okay? And so this is somehow what we have. And we realized that actually to study this vertical dynamics is useful to just attach an accelerometer on the quasi-2D cell, and with and taking the signal of the acceleration of the cell and filtering it, we can actually resolve the collision that happens between the grain and the plate. So for example, here I'm showing you one double period of the system for two different vibration amplitude. And so if I just plot one time double period, you don't see any relevant difference between the two cases. While if I start to superimpose more and more double periods, you start to see that for this amplitude you have a sort of regularity in the collision, while here they look more random. But then if I superimpose a lot of double periods, I do see that indeed for this amplitude the collision between the grain and the plates happen always at the same time for each period, while for this other amplitude they are completely randomized. And I can basically extract a sort of degree of synchronization from this signal and plot them as a function of the amplitude. And what we observe in the vertical dynamics of a single particle within the plates is a transition between periodic motion and between periodic and chaotic motion, which is indeed a hallmark of nonlinear dynamics in mechanical system. And now that we know that in the vertical dynamics there is this phenomenon, we can look with different eyes what is going on in the horizontal dynamics in terms of energy absorption. And we do see that indeed this non-monotonicity of the critical area fraction that is given by the fact that I can go back and forth between the two phases moving as a function of the amplitude is somehow correlated with the transition between highly synchronized state and asynchronized state as a function of the amplitude for single particles. And this is because somehow we can again understand this thanks to this interplay between synchronization and energy transfer. This is why if particles are synchronized, again, if particles are synchronized between the plates, they will tend to undergo collision in a planar configuration. So mostly being at the same height, because they are both in phase with the plates, so they will be also in phase with themselves. And this kind of collision, in this geometrical configuration, they transmit less energy from Z to XY. So it's similar to what I was explaining before. While when the particles are asynchronized, they will tend to undergo collision that are off-planar collision are much more efficient in exchanging energy from Z to XY. So basically now you can basically retake all your data and plotting and taking into account the degree of synchronization as a function of the amplitude, that indeed now you obtain a phase diagram that is much simpler with somehow a monotonic trend of the critical packing fraction. So to conclude, again, this in the thesis of Raphael Mer, we also studied also this phenomenon within simplified models and kinetic theory, and we were able to reproduce this effect of the effect on the critical packing fraction of the synchronization. So you see that you can somehow take into account synchronization effect in these models and predict the fact that the critical packing fraction can increase with the degree of synchronization. So synchronization makes basically the energy transfer less efficient. And so to conclude, we saw that there is this idea that synchronization in the vertical dynamics affects the energy transfer at collision, and in turn change the transition point of this phase transition. And what we would like to do next is studying this kind of energy burst that you have in the horizontal dynamics if you place yourself close to the critical point. This is a kind of there is a kind of avalanche dynamics that somehow you can do also. You can do here some analogies with like models where you have avalanches in, for example, in elastoplastic models and this kind of system. So now that we saw that, actually I wanted to show you something about hyperuniform fluids, but then while preparing this seminar, I also obtained some preliminary results on the idea of vibrating cohesive granular matter. So I decided to go on this direction. But if you're interested on this concept of hyperuniformity in active systems, we can also discuss about that. So the idea of taking into account cohesion and vibration naturally arises by noting that somehow cohesion is something that hinders the ability of a granular system to flow. So for example, here you can use water to make a granular system more cohesive and build, for example, a castle of sand. While on the other hand, vibration usually helps the system to flow. So you have, for example, this phenomenon of vibrofluidization. And this effect of vibration on granular forces is very important, both for, I think, things that happen in the natural environment and also for application. So what I did is considering this system of cohesion control granular matter that exploits the fact that there is a polymeric material that is able to adhere permanently on glass surface. So you can coat glass grains with this polymer coating that gives to this grain a stickiness property, sticky properties, and then actually you can also control the cohesion by controlling the thickness of this coating. And what I did is I consider this system arranged in relatively thin layers. Then I put this on the experimental setup with the vibrating substrate, and I took some images from an inclined view. And this is the typical dynamics that I observe. So here you see that you have this thin layer of cohesive granular matter vibrating on this surface. It is mostly arranged on mostly double layer. So it's a layer made of a height of two grains. And you see that there is some standing waves that can be excited on this membrane. This is because it seems like when you see it, it seems like a living membrane. And remarkably, the system stay cohesive. It's not destabilized. It's not by the vibration. Here I'm imposing very strong vibration. So without the coating, I would just have like a granular gas going everywhere. So when I saw that, I say, okay, let's see how the system relaxes during vibration if I prepare it in different initial configuration. So, for example, I try to initialize the system in a flattened configuration in which I mostly have a mono layer, so it's spread larger. And then I see what happens as a function of time. It's important to remark that in this configuration, without vibration, you can expect two things. Either the system stays there because it's trapped in a metastable configuration and it doesn't flow. Either it flows a bit more because of gravity and maybe it spreads a bit more. While what I observe is that thanks to vibration, the system contracts back to a stable configuration. And I found this is interesting because somehow the system, I mean, the material realized that it has an intrinsic elasticity thanks to the fact that with vibration, it can explore the configuration state. So the grains somehow realize that there is more efficient to stay closer. Okay, but you observe this just thanks to the interplay of cohesion and vibration. So when I say that, I say, let's see what happens if I start with a fractured layer. So here you can ask yourself, okay, the fracture will somehow, is enough to destabilize the system and make it like, and destroy with vibration, or will I observe something else? And indeed, I observed that thanks to the vibration, the system somehow explore the configuration space and is able to self-heal. So this is just a preliminary investigation, but somehow to me this is somehow already I don't know some results that really tells us that this interplay between cohesion and vibration is something very interesting to explore. So for example, we can think about varying the amount of cohesion between the grain and at the same time the vibration, and see how the interplay of these two change the emergent phenomenology. We can, for example, pen also with the cohesion between the substrate and the grains, and we can somehow revisit some experiment that have been done with the yield stress fluids that consider how somehow how the yield stress somehow affects the macroscopic emergent properties of the system. So now I arrive at the end of the seminar. I want to acknowledge somehow the main collaborators in this study, which are the two PhD students, Raphaël Mer and Etienne Fayenne, that focus mostly on the theoretical part and the numerical part with the coarse-grained models. Then also Frank Smallenburg and Giuseppe Foffi that had this original idea of realizing colloidal structure at the macroscopic scale with vibration instead of temperature, and of course the experimental colleagues from the MOA group that was helpful in somehow helping me in this transition from theory to experiments that I did during the postdoc, and also Emmanuel Trisac that helped us with the kinetic theory part in some part of the project. And of course, now thank also for your attention, and if you have questions, I'm happy to answer.
Do you have any questions? How you measure the synchronicity of one particle? Because what I think to understand is when you plot for several double periods, does it mean you change the frequency of vibration or no?
No. So basically, here you for this plot you have a fixed amplitude, a fixed frequency, and then you just measure the acceleration signal coming from the accelerometer as a function of time. Then you take this signal and you superimpose the signal 2 periods at a time. So here you have the first 2 periods. Here you have the first 4 periods plotted one on top of the other, and here you have the 100 double period plot superimposed one to the other. This is a way just to visualize that collision happens at the same point within a same period. Okay. Mm-hmm. Yeah. Mm-hmm.
And so maybe the vibration is just reducing the friction between the material and the surface and allowing surface tension to act. For example, you can interpret the first state as a balance between the friction on the plate and surface tension, and just by vibrating, you reduce that and allow the system to.
Yeah.
Is that your interpretation, or you seem to suggest was more something changing the effect of rheology?
I don't know, I mean, this is something we should test by, for example, changing the friction without applying vibration and see if you observe the effect. To me, at least when you look at the experiment, I really have the feeling that is more like a matter of stability of being in a monolayer or of a multi-layer. So I have the feeling that if you are in a monolayer, you start to feel this kind of oscillation. So your grains are doing like this. And the feeling is that sometimes you have grains that escape the monolayer and jump on top, and then they are trapped there. So it's more this kind of stability of with respect this kind of mechanical excitation. But somehow the analogy with surface tension, I mean, I do see that it is possible. So I mean, once you treat this phenomenon with grains, I mean, the approach is also the thing that maybe you first find a mechanical argument that explains the phenomenon and then try to map this in an equivalent surface tension. So that's the thing.
Hello, thank you for the seminar. I have one question relating to the first two parts of the presentation.
Mm-hmm.
Actually, I'm struggling to understand how equilibrium thermodynamics can help quantitatively describe this system. So for instance, for first order phase transition in equilibrium thermodynamics, you have the relation between latent heats and the shape of the coexistence curve.
Sorry, the shape of, I don't know. The
coexistence curve.
Yes.
Diagram. Do you have similar results here? Or other question, close to the critical points, you have critical exponents.
Yeah.
Do you expect to have the same exponents here?
I mean, the critical exponents are kind of difficult to measure to be measured in this setting because you're a relatively small system, and we didn't address this kind of quantitative analysis. Somehow, the analogy for us is more towards the idea that if something, so at least for phases like in this system that are R-core, that interact with R-core interaction. So basically, where the thermodynamic stability is driven by entropy. So basically, you don't have energy contribution. They are in phases stabilized by entropy, which just means that this configuration at this packing fraction are the most probable. And so by exploring the configuration space in a way that is compatible with equilibrium, at the end of the day, you will just observe the most probable state. So this is somehow the fact that you realize the same geometrical constraints at the macroscopic scale, and then you let the system explore the configuration space with vibration, does not somehow allows you to explore the configuration space in a way that you arrive to the same stable structure. So you still observe the most probable phase. So we didn't go so much beyond that, because somehow the idea is that you can still think of reaching the same target structure if you carefully tune geometry and vibration in such a way they are almost Brownian-like. So that's the thing. But yeah. Yes. Yeah. Yeah. Okay. Okay. First, regarding the driving we impose, basically we vary the amplitude and frequency, but the idea is that somehow, if you take hardcore equilibrium systems, you know that basically you don't have any effect of the temperature. So if you take hardcore interaction at equilibrium, you have your potential that is zero if particles do not overlap, and is infinite when particles overlap. So when you take the Boltzmann weight e to the minus beta v, you have 0 and 1. So basically, the temperature does not really play any role in the phase diagram. So only geometry is important. Somehow, at the macroscopic scale, it's kind of the same. The thing is that you need sinusoidal shaking, which is gentle enough to make the system not triggering strange non-equilibrium effect like side segregation, particle going everywhere in the z direction, but at the same time strong enough to make the particle explore its configuration space. So the take-home message is that as long as you are able to realize such a non-equilibrium driving that respects this condition, then this mapping is allowed. So we were not interested in studying what is happening as a function of the driving parameters. We were just interested about having good ones to explore this analogy. But the thing is that if you shake too much, they go everywhere. If you shake too gentle, they just remain stuck in the configuration. So that's the thing. On the numerical side, yes, we allow for dissipation. So here we use the Hertz-Mintlin contact model. So you have the interaction between the grains. You have Hertzian repulsion that are conservative. Then you have a normal viscosity, the dissipate energy in the normal contact. And on the tangential direction, you have also like dry Coulomb friction. And so you allow for, they are really somehow realistic contact models that you use also for DEM of realistic systems.
Thank you for your nice talk. I have a question maybe following the same lines. If you go back to the assembly self-assembly system, and yes, this one, so you are saying that it's tricky to find the right amplitude to get the system to move, but not too much.
Mm-hmm.
But could you play on the size of your two assembly and the amplitude at the same time to reach the same type of equilibrium?
Okay. Thanks, because somehow I think you. The thing is that if you play with this you don't really want to play with these parameters, because these parameters somehow are also the one that determines which phase you stabilize. So you don't want really to play with the size ratio and the fraction of small spheres. What we found that is really this is a technical point, but what we find we did. I don't know if you noted, but basically between this experiment and this one, we changed the beads. These are polyamide beads, so made of like plastic, and these other are steel beads. So this system was like somehow easier to handle, because the geometrical state point we consider as a high concentration of small particles. So when you vibrate these, actually the big particles can move because they receive a lot of energy thanks to the collision from the small particles below. So in this case, you can have a you can reach, this is an optimal case because you can reach a relative high mobility in XY with gentle vibration, because a lot of energy transfer is given by this collision between big and small. In this other state point, we have our target state point. You have the same amount of big and small spheres. So somehow this system is much more. It has less this effect of Z to XY energy transfer thanks to the small beads. And for example, indeed, when we did this experiment with steel particle, we were, we find that we had to increase the amplitude, so the particles were start to going everywhere. Was a mess. So we solved this problem by sandblasting our surface. So you have like a rougher surface. So the rougher surface itself is able to transmit more the energy in the XY when you vibrate vertically. But then if you take a rough surface and you put steel particles, they flatten it because somehow this is aluminum plates, so steel is harder than aluminum, you will flit. And so we solve this by using plastic beads. And so you can play a bit, with the material properties to still have this kind of dynamics that gives you the correct equilibrium pattern. Sorry for the long reply, but I mean, the binary condition, of course, they are just a square boundary condition. And but in simulation, we did it with periodic boundary conditions. So somehow we checked that it's not. I mean, yes, here you have it, but the phenomenon is robust with respect to the boundary condition you choose. Okay. 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 Okay.
Thanks again for the seminar.
Thank you. Thank you. Thank you.